Assalamu alaikum. I'm Abdul Muqeet, and I'm going to discuss about the lecture 4, that is discrete Fourier transform, lecture 4 of DSP. So in this lecture I'm going to show you how to find a discrete Fourier transform of a given sequence. So let's start. So first of all, let's discuss what is a Fourier transform. A Fourier transform basically is an important image processing tool which is used to decompose an image into its sine and cosine components, and the output of the transformation represents the image in the Fourier or frequency domain, while the input image is the spatial domain equivalent. So basically it's an image processing tool. And in discrete Fourier transform we talk about signals that are in discrete form, or here you are given a sequence. So how to find a discrete Fourier transform of a sequence, let's study. So first of all, let's derive out our formula for discrete Fourier transform. Here we have for continuous times Fourier transform for a continuous signal. If we use omega naught is equals to 2 pi by t naught, in discrete we have t is equals to nt. So t naught is equals to nt. So if we replace the values, if we replace the values over here with the discrete values, we're going to get the formula x of k is equals to summation n is equals to 0. Integral is converted to summation in discrete, and x of t is converted to x of n, since we are talking about the discrete sequence. And here e raised to power minus j, where omega naught is equal to 2 pi by t, so we write it over 2 pi by t, but here t naught is equal to nt, so the t and t gets cancelled, so we get j 2 pi k n by n. So this is basically the formula we are going to use to find the discrete Fourier transform for a given sequence. Let's talk. If we consider, you might be thinking that where that 1 over t naught go. So basically 1 over n here in discrete, 1 over n we should say, is basically used. It is a scaling factor. It is a scaling factor. How it's a scaling factor? Let's suppose we had the following Fourier sequence. So if we multi, and let's suppose this was the since 1 2 3 4 values, this was the number of samples 1 by 4. So when we multiply it, we get 1 2 3 4. So basically you can see over here that the difference remains the same, so it's just a scaling factor, so we can remove 1 by n over here. So we get the formula x of k is equal to summation n is equal to 0 to n minus 1, where capital N is basically the number of samples, number of given samples, x of n e raised to power minus j 2 pi k n over n. So to find DFT, you need to remember this formula. Obviously we're going to consider an example here. Let's suppose we have the example over here where a sequence is given x of n is equals to 1 3 0 and 2. We need to find its DFT. So basically how many samples we have? 1 2 3 4 4. So n is equals to 4. N is equals to what? 4. And k is always equals to 0 1 to so on n minus 1. So here we have 4 minus 1, that is 0 1 2 3. So we're going to find DFT at k is equals to 0, k is equals to 1, k is equals to 2, and k is equals to 3. So it's very easy. It's basic technique here. We just need to put values in the formula. At k is equals to 0, we have the formula x of k. So x of 0 is equals to summation n is 0. Obviously n is 0 to n minus 1. We're going to start from 0 to n minus 1. X of n is 1 minus j 2 pi. Here k is equal, since k is equal to 0, so we can put k is equal to 0. So you can see clearly that if there is even a single 0, it could convert all this expression to 0. So we can directly write e raised to power 0, as you can see. So and then n minus 1. Here n is 4, so 4 minus 1 is 3. So summation 0 to 3 x of n e raised to the power 0. E raised to the power is equal to 1. E raised to the power is equals to 1. So 1 multiplies x of n, we get x of n. So just need to apply the summation over here. First with the n, first the value of n is 0, x of 0, x of 1, x of 2, and x of 3. X of 0 is over 1, x of 1 is 3, x of 2 is 0, and x of 3 is 2. We sum all these and we get 6. And for that was now we're going to find at k is equals to 1, since x of k x1 is equal to summation 0 to 3. Sorry for the sign, it's like this: summation 0 to 3 x of n e raised to power minus j. Now you can see that since k is not 0 it's 1, so 2 pi into 1, it's 2 pi, and divide by 4, so 2 and 4 gets cancelled, we get minus j pi by 2 n. Now we're going to apply the summation 0 to 3 for 0 x of 0. When 0 multiplied by this, we get e raised to power 0, which is equals to 1. Then for n is equals to, after 0 we get 1, so x of 1 e raised to power minus j, n is also 1, so minus j pi by 2. And similarly x of 2 will multiply by 2, and x of 3 multiply by 3. So here I have, as you know, we have the Euler equation that says e raised to the power minus jx is equal to cos of x minus j sine of x. So I have used this formula to um, get e raised by minus j pi by 2 to minus 3j, and similarly for here. So we will get 1 minus j. And similarly we're going to find for at k is equals to 2. As you can see, we're just plugging k as 2, and that's we're following the same procedure, and we're going to also follow for the same procedure for k is equals to 3. So we get for frequencies, that is 6, that is 6, 1 minus j minus 4, and 1 plus j. So let's talk about I'm going to tell you about a shortcut to find this frequency. We know that maximum frequency is equals to 4. As you can say, maximum frequency is equals to 1302, and n is equals to 4, so we have max frequency 4. And we know that according to Nyquist theorem, sample rate is equals to 2 multiplied by f max, so that we can, so according to Nyquist theorem, we find x of 2 is the max frequency. X of 2 is the max frequency. Where is x of 2? There it is. X of 2 is the max frequency. So what basically is that, let's suppose we had for Fourier values for x of 0 is equal to 6, x of 1 is equal to 1 minus j, and x of 2 is equal to minus 4. We know that minus 4 is the maximum frequency. After the maximum frequency, all the values will be the conjugate of the previous one. So if you can see over here that minus 4 is the f max. Okay, so here the next value will be the conjugate of the value that is above the maximum frequency. So that's, so after maximum frequency, the next values will be the conjugate of the values above max frequency. So that was, so this is how we find the Fourier transform or discrete Fourier transform of a signal.